Alright, we're going to look at some stuff on Chapter 9 today. So Chapter 9 deals with what we call significance testing. Now, significance testing encompasses a lot of different things in statistics, but it's really talking about, is there something we can say meaningful about a population parameter? Is there some statement we can answer based on some parameter? So here's an example. So we're going to collect some data. So if I have some research question I want to answer, I collect some data about my topic. And then what we want to see is basically what I see, how does that kind of mesh with what I'm claiming about this parameter? So if I look at this first example, it says if some expert claims the proportion of all students who are getting enough green vegetables in their diet is 56%. So someone is claiming that 56% of all students are getting enough green vegetables. So how could we test this? Well, obviously I would want to collect some data. And come up with a statistic. And then we can use that statistic to compare to what is being claimed. So let's say we do that, and I did that. So I collect a sample of 100 students, and 90 of those 100 say they do not get enough green vegetables. So that is going to be a sample, so that is p hat, and that's going to be 0.9. So if we're asking, what does that say in relationship to this claim? So this expert is saying, well, 56% of all students get enough who are getting enough green vegetables, and this is saying 90% of the sample got enough green vegetables. That's obviously a lot higher than what the expert is saying. So what does that say in relation to the claim? So do you think that this is enough information to say, well, maybe this claim up here is incorrect? The question is, yes, it certainly could be. It could be the fact that I have collected data, and that data is basically convincing enough to say the previously thought notion of the proportion being 56% is not correct. The other idea could be is maybe this really is correct. Maybe it actually is 56%. And my 100 students I collected were just a really, really different sample. Their sample statistic is just really, really far off from what the actual value is. Both of those are actually a possibility. And this is what we kind of deal with when we talk about significance testing. We're trying to say something meaningful about these claims, about this statement here. We're basically trying to say, is there evidence to refute that statement? There either is going to be evidence to refute it, or there's not going to be evidence to refute that. But this idea that we either have a rare sample or evidence against the claim is a really, really important point. And that's kind of the big point of all significance testing. So in a significance test, all information's against the claim. And we'll have special names for these claims here in a second. But in general, we never will show evidence for this. We won't try to prove this true. We're either going to prove it's not true or not be able to prove it false. So our two cases with these is we're going to prove that this claim is wrong and it's good evidence against it. Or what could be true and what we really can't prove is that the claim is correct and we found an unusual sample. So we're really just going to figure out how much evidence is there to show that this claim is wrong based on our sample statistic that we calculate. So to do this process, to do a significance test, there's lots and lots and lots of steps. So we're just going to kind of, in this first section, go through some terms, talk about how we set this up, what the first steps are in doing a significance test. So the first thing we're going to do is we are going to make what we call hypotheses. Now, we just give basic names to what we just talked about above. So the null hypothesis is our expert's claim that we talked about from above, okay? So the null hypothesis says typically there is not a difference between a parameter and a given value. And we have some notation we can talk about this. Generally speaking, how we denote a null hypothesis is we denote it with H sub 0. Okay, so a sub-zero is a typical way to say null. So the null hypothesis H sub 0, and it's always saying there's not a difference. Well, if there's not a difference, that means it's always equal. So there is not a difference between a parameter. Let's say it's P, and let's use our green vegetable example from above. So P is equal to 0.56. That is claimed by some experts. There's no difference between the parameter and what they're saying. You could, of course, do this with a mean as well. You always use the parameter symbol, so P or mu. So I could say mu equals 8. So some expert is saying the average, I don't know, hourly rate for a employee is $8 an hour. So that could be a claim, something that is saying these are true. And so what we do is we have these alternative hypotheses that try to disprove it. And these basically say there is a difference between the parameter and the given value. So these can actually be more varied. So instead of saying that P is equal to 0.56, we basically want to disagree. So one case you could say is you could say the alternative, which we typically denote H sub A, H for hypothesis of alternative, we could say, well, I don't agree with that. I think it's not 0.56. So this would be an alternate view. This is basically a disagreeable statement. You say it's 0.56, I say it's not. You could also be more specific in your statement. Instead of saying not equal to 0.56, say, well, I don't think it's 0.56, but in fact, I think it's bigger than 0.56. So this would be another example of an alternative hypothesis. And you only have one. You don't want to test all these, but you'll have one for each problem. You could also say, well, no, I think the proportion that eat their green vegetables is less than 56%. So these are some examples of alternative hypotheses. Same thing for the mean. If someone is saying that the average rate is $8 an hour, maybe I say, no, you're just not right. It's not $8 an hour. Or I could say, all right, well, it's more than $8 an hour. Or I could say it's less than $8 an hour. And the way you'll do these in problems is you will basically look what the claim is saying. Is there evidence to show that the mean salary is less than 8 or bigger than 8 or not 8? So we typically give names to this, so we'll hear these terms a lot when we talk about one-tailed versus two-tailed hypotheses. Essentially, if the alternative hypothesis is the not equals, then we call it two-tailed. Now we call it two-tailed because it has basically two ways to be true. It could be smaller or bigger than the given value. So that's why we call it two-tailed. So when you hear a two-tailed test, we know that our null is going to be, I don't know, mu equal to something, and our alternative is going to be whatever not equal to that. A one-tailed would just mean it's going to be less than or greater than. So let's just practice writing some of these hypotheses. So we're going to try to write the null and alternative hypotheses for these situations. So a researcher thinks that if expectant mothers use vitamin pills, the birth weights of babies will increase. So that's our first big word, increase. The average birth weight of the population is 8.6. So some expert is telling us what the value is, and we're saying, well, if the mothers take these vitamin pills, the weight will increase. So the alternative is basically what is being claimed. Now this is a mean because it's talking about average, so we're going to use the symbol mu. So in general, we say the average is equal, mu is equal to 8.6. The alternative, we are saying when we take these vitamins, it's going to increase the mean. So we're going to say the mean is going to be greater than 8.6. So that would be an example of a null and an alternative hypothesis. Someone's saying it's 8.6. We're saying, no, when we take these vitamins, it's going to be bigger. The next one says an engineer hypothesizes the mean number of defects can be decreased in a manufacturing process of using compact discs by using robots instead of humans for certain tasks. The mean number of discs per 1,000 is 18. So again, this is talking about the mean, so we'll use mu. Most of these talk about mean, but you could do a proportion just the same. So the mean number of defects in some process is 18. And we're saying if we use robots, that's going to decrease. So our alternative is saying once we implement the robots, the average number of defects is going to go down. All right, so this last one, or the next one, says a psychologist feels that playing soft music during a test will change the results of the test. So he's not sure if it's going to go up or down. So this is again where we're going to do the two-tailed test. Pretty obvious because we're not sure. It's the change. Change is a pretty key word where we don't know if it's going to go up or down. It's just going to be different. So the average test typically is going to be 73. So if we start playing music, what's going to be different? So we're going to say it's not going to be 73. Maybe it'll be a distraction and won't work. Maybe it will. This last one says, all right, a zoo official feels that the time spent by the reindeer flying is 2 hours a day. So that is a statement. So no, they're saying the average number of hours flying is 2 hours a day. Now, it doesn't really say if our alternative should be bigger than or smaller than. If it doesn't say, if it's something like this, and you just want to test the claim, we always default to the two-tailed test. So if it doesn't say anything, if it just tells us a statement of truth, if we're going to do a significance test, then we always use the alternative as the two-tailed not equal test. Okay, so now we have our hypotheses. What we're going to try to do is we're going to try to figure out how much evidence there is against the null for the alternative. So we're trying to figure out how much evidence is there to say this one's false. And if that one's false, then obviously this one's true, because these are basically contradictory statements. So when we're trying to find this evidence, we're trying to find out how much evidence there is for the alternative based on the null. We can actually calculate that number by using what's called a p-value. So p-value is one of the biggest things we're going to calculate in this chapter. And a p-value is simply going to be the probability, assuming that the null is true, that the statistic would take a value as extreme or more extreme than the one observed. So let's go to our reindeer problem. Let's say, all right, let's assume this is true. Well, I get some sample mean, let's say it's 1.5. A p-value is saying how rare, what's the chance that I would see this statistic, this sample statistic, if this is true. So obviously if the p-value is small, there's not a very good chance I'd see that sample if the claim is true. So then you'd probably say, well, this is probably not true. It's not equal to 2. So that's what a p-value does. So in very simple terms, a p-value will determine how rare a sample you have found if the claim was true. So a small p-value, if your p-value is really small, and we'll figure out how to calculate that in future sections, then there is good evidence against your null, and then for the alternative. So if your p-value is small, let's say I did this p-value and I calculate, I got 0.0001. That's pretty small. Well, if that's small, then pretty good evidence that that is not true. And so then this one would be true, because that's the alternative. So if there's evidence to show it's not 2, well, then it's not 2. So if your p-value is large, that means there's not good evidence against the null. So you can't say this is false. You can't put that big X through the null because we don't know. So if your p-value is small, that's actually good for us because it says the null is false, the claim of the expert's not true, and whatever we are saying is true. So we will go through, we'll calculate lots of p-values in the future, but for now, if you have a small p-value, remember that's good evidence against the null. Now the big question is how much evidence is good? For this p-value, how small is small? That's always a good question in math. How small is a value to be considered small or large? Well, we actually have a value, and we call that value the level of significance. Okay, the level of significance is going to tell us how small the p-value has to be. Okay, so the level of significance is going to be the maximum chance to reject the claim incorrectly. So this is the maximum chance we're going to allot for that. So if it's 0.05, that means 5% chance. And so our p-value has to be smaller than this value to reject the claim. So we sometimes refer to this as rejecting the null or failing to rejecting the null. Rejecting the null says we are stating evidence against the null for the alternative. Okay, so we will reject the null. We'll say it's not true if we are rejecting the null. We do this, and this is very important, this is done when the p-value, and this p-value, that chance of finding a rare sample, is less than our level of significance alpha. So again, level of significance is denoted by alpha. So if our p-value is smaller than that level of significance, then we will reject the null. The other option is to fail to reject the null. So failing to reject the null means there is no evidence, or not enough evidence, against the null. So if there's not evidence against the null, and so there's none for the alternative. So it's basically inconclusive. So we do this, we fail to reject the null. This is done when the p is bigger. P-value is bigger than our level of significance alpha. So if you have a small p-value, again, how small? It has to be smaller than this level of significance, which is quite honestly a lot of times 0.05. If it's small enough, then we can reject the null and be for the alternative. Otherwise, we have to fail to reject the null and just say, well, we don't really have evidence for anything. So let's look at an example of this. So this says a company has developed a new AAA battery. It's supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company wants to make sure that they really do last longer. Based on years of experience, the company knows that its regular AAA battery lasts for 30 years or 30 hours of continuous use. So we picked 15 new batteries and tested them continuously until they're completely drained. So a significance test is performed. So here are our hypotheses. Obviously it says that mu equals 30 because that's the claim of the company. That's the existing value. And now the new claim is that it's going to last longer than that 30, because if it doesn't last longer than that 30, then why are we making these? So we do some math, we get some stuff, and we get this p-value, right? So based on our sample, we get a p-value of 0.0276. Now this is an interesting question because our level of significance really will make a difference. So if our level of significance is 0.05, then the p-value is less than the level of significance alpha. If that's true, we would reject the null. So we reject the null hypothesis. We're basically saying this claim is incorrect. So if that claim is incorrect, then what we'd really be saying is we would say there is evidence based on this p-value that the mean life of the new batteries is over 30. Now, this is a great time to kind of mention what we mean about great or greater than. Now, just because something's bigger than doesn't mean it's a lot bigger than. 30.1 is bigger than 30. So it just means that what we're showing is shown to be statistically significant. So the results we're seeing are not due to chance, but they do not have to be large. They don't have to be big in scale. They just have to be statistically significant. So there is evidence that this new battery life is, the mean life is over 30. But interestingly enough, it really is based on our perspective, because if I look at an alpha of 0.01, then in this case, the p-value is larger than alpha. So our results will switch. We would say there is not evidence that the mean life of the new battery is over 30 hours. So that is quite a difference. There's a big difference between what your level of significance is, because it's all about how much error you want to take. And the first one was 0.05, so I'm allowing a bigger chance that my results are wrong, so whatever I conclude could be wrong. In this case, I'm giving less of a chance of that happening, but I don't have conclusive results. I have basically says there's not evidence that the new mean life of the new battery is over 30. So this p-value is a very interesting creature. When we get it, and we know whether we reject the null or we don't reject the null, we fail. So this one would be fail to reject. It really depends a lot on what your level of significance is. And really, the researcher would choose that, or in a statistics class, that's generally given to you in a given problem. All right, the last thing I want to talk about is what's called type 1 and type 2 error. And these are errors that can happen in a significance test, and we try to mitigate them. One of those is what we call a type 1 error. So a type 1 error is obviously, in both of these, we're doing something wrong. So in a type 1 error, we're rejecting the null when it's actually true. So if I say that my null is mu equals 4, and my alternative is mu is not equal 4. So if I find a p-value and compare it and say, well, that's not true, this one must be true. Well, if that first statement was actually true, I shouldn't be rejecting it. So this is what we call a type 1 error, when we're rejecting the null when it's actually true. This rejecting the null when it's actually true is actually covered by our alpha, our level of significance, and our p-value. So that is something we account for. A type 2 error is when we fail to reject the null when it's false. So if the null was false, let's go ahead and use the same set of hypotheses. Mu equal 4, alternative mu not equal 4. So if the first statement's false, if mu really isn't 4, then we should reject that and claim this one. If we don't do that, if we fail to reject when the first statement's actually false and we don't reject it, then that's what we call a type 2 error. So here's a pretty famous little chart that kind of summarizes it. So if the null is true, so if the null truly is true, if we say it's false, if we reject it, that's called a type 1 error. We shouldn't do that. If the null is true, we should fail to reject it. That's correct. We shouldn't say it's false, because all you can do is say it's false, the null is false, or we can't show it's false. So if it's true, I shouldn't say it's false. But same idea, if it's false, I should reject it. If it's false, I should say it's false. But if it's false, I shouldn't fail to say it's false. I shouldn't say, well, I don't know. I should say it's false if it is false. So that is the idea behind type 1 and type 2 error. And again, it's just something kind of exists in a significance test. It's not something we really speak to in every problem, but it is an error that is always kind of prevalent and something you have to consider when you're doing authentic research. So let's look at this question and kind of talk about type 1 and type 2 error. This says if a researcher claims that the average number of stereotypical behaviors by the water bear is 3 per 10,000 years. So we are saying the null, mu equals 3 per 10,000 years. As a water bear fan, I disagree and think the average is much higher. So my alternative is going to say, well, that mean is higher than 3. So that's my null and alternative hypothesis. So what I want to do now is write what really would a type 1 error be, what would a type 2 error look like in this case. Okay? So a type 1 error would say this. A type error would say, I'm going to reject this when it's actually true, So this would be rejecting mu equals 3 in favor of mu greater than 3. So we're basically saying the first one's false, evidence for this one, when in truth, when mu did equal 3, in fact. Now again, we never really know what mu is because remember, mu is this parameter that holds for the whole population. So it's really difficult to know what it is. That's why it's hard to really quantify type 1 and type 2 errors. But if you reject the null when it's true, that is a type 1 error. So when it's true, that's a type 1 error. So a type 2 error, let's go ahead and write these hypotheses down again. So mu equal 3, mu greater than 3. So a type 2 error, I should reject the first one, but I don't. So a type 2 error is when you fail to reject, the null, which is mu equal 3, when in fact mu equals 3 is false and mu greater than 3 is true. So when you fail to reject, when you should have rejected, the correct decision would have been to cross this out and say this is true. Well, if you don't do that, that's a type 2 error. Just like a type 1 error is if you do reject when you shouldn't have rejected, that's a type 1 error. So again, kind of a thing that happens in the background, but this is an error that is really prevalent in any kind of research. All right, so that's just kind of a little background on significance testing. We will run a lot of examples of these on proportions and means, and you'll get a really good idea of how to calculate this p-value, how to summarize these kind of problems.